So 7.3a is just going to introduce a handful of more identities for you. As you can see, it's the double and half angle identities, but the things I'm going to ask you to do, our lesson goals are exactly the same: evaluating, simplifying, proving, etc., etc., etc. So just like the other videos, I'm not going to really show where these formulas come from, but if you are interested in where these formulas come from, please definitely let me know and I'll gladly show you. I will say, though, that the bulk of all of trig identities come from the sums and difference formulas, which was the hard work. So I'll just verbally tell you, how do we get the double angle formula for sine? Well, we already know the sums and difference formulas, right? So we should know that sine of 2x is the same thing as sine of x plus x. And if you run through the double angle formula for sine, the sums formula for sine, you're going to get the double angle formula. And that's basically true for all of these. How do I get the double angle formula for cosine? Well, it's just cosine of x plus x, and then you run through the sums formula. Do know, though, that cosine has 3 variations, because when you do use the double angle formula for, the addition formula for cosine, that you're going to get some squares involved. And of course, with Pythagoras' identity, depending on what you substitute, you can get one of these 3 variations. So the first variation is gotten from just simply doing the sums formula for cosines, and the other 2 variations are gotten from using Pythagorean identity. So feel free to pause the video if you're copying this down. But the next set of identities to give you are the half angles formulas. And again, these guys here come straight from the cosine, the double angle formula for cosine. So if you were to take each of these individual equations and solve for the respective trig functions, so for example, if I solve for sine in this version, you're going to get this guy. If you solve for cosine in this version, you're going to get this guy. And sometimes it's sort of nice to, instead of thinking of double angles, you think of half angles, because, you know, sometimes angles do get smaller. Do note, though, that it will involve taking a square root, and when you take a square root to solve an equation, it's going to be plus or minus. The choice of whether or not we keep the positive or the negative will be dependent on the original angle. It'll be dependent on whatever angle we started with, and depending on what quadrant that is, they'll tell us positive or negative. Other than that, other than being able to know that these formulas exist, the tasks that they're going to ask you to do are just the same tasks we did yesterday, which is the same task we did in Unit 6. So what are some things that you'll most likely see? You might see this example here. Say if I tell you that the cosine of some angle x is negative 2/3, and I tell you that x is in quadrant 2, I want you to find cosine of 2x and sine of 2x. Well, this is the key here, the information that they give you. So just like yesterday's lesson, just like in Unit 6, if I give you an exact trig ratio, you can always draw a triangle. Now, different teachers do it differently. I personally don't care about the negatives until the very end. So here's my right triangle. Here's my angle x, that's a very ugly x. And they tell me that the cosine is 2/3. I'm ignoring the negative for now. And then I can use Pythagoras' theorem to figure out the remaining side. So the remaining side is 9 minus 4 is square roots of 5. So now I can answer the question. So let's start with cosine of 2x. So I'm asked to find the cosine of 2x. I have lots of variations for the double angle formula for cosine. It really doesn't matter which one you use, you'll get the same answer. I am sort of like lazy, and I want to use a version that that involves information that I are already given. So since they right out the bat give me cosine, that's the only numerical information I have, let's use the one that only uses cosines. In other words, I'm going to use this variation here. No reason why one method is not better than the other, but this is, I think, the quickest. So according to the double angle formula, I know that cosine of 2x is 2 cosine squared x minus 1, and they already told me what cosine of x equals. Cosine of x equals negative 2/3. Now the negative doesn't really matter because we're eventually going to square things. So that gives us what? 4/9. So that's 8/9 minus 1, which is negative 1/9. Right? So that's what cosine of 2x equals. Now I have to find what sine of 2x equals. And again, I'm just going to follow the double angle formula. And according to the double angle formula, you can look back in your notes. I'm not going to bother scrolling up again. It's going to be 2 sine of x cosine of x. Now, fortunately, these pieces here we should be able to figure out because we have a complete triangle now. So looking at this picture here, I know that the sine of x is going to be radical 5/3, but we always have to be mindful of the quadrant. According to the problem, quadrant is 2, and a good thing because sine is positive in quadrant 2. Cosine, they've already told me, was 2/3, and of course, since we're in quadrant 2, it's going to be negative. And that's it. You just basically do math. So if you multiply straight across, you're going to get negative 4 radical 5/9. So that's what sine of 2x equals. So that's one thing that you'll be asked to do is, is to be able to, well, basically just find stuff, calculate it. Yeah, not much more to say than that. And like I said, Unit 7 is just following instructions. What else did we do? We did simplifying, right? So suppose they asked you to prove, right? So prove that sine of 3x over sine of x cosine of x is equal to 4 cosine of x minus secant of x. I'm going to start on the left-hand side because, again, anytime that my angle is not a simple x or a theta, whatever letter you use, that's what I call complicated. Now, this is a triple angle, and you're probably going, well, we didn't have a triple angle, Mr. Vo. You only gave us double and a half angles. Well, that's true. So the idea is that you want to decompose or rewrite it in terms of what we know, and I hope everyone can agree that 3x is the same thing as 2x plus x. So now we have a sign of a sum, so we can use the sums and difference formulas for the numerator here. So that's sine of the first guy, cosine of the second guy, plus cosine of the first guy, sine of the second guy. Now notice how we got one giant piece here. This is one giant fraction. And I know we should end up with two separate pieces. So that might be a signal to me to split apart the fraction. On the other hand, I know, looking at my end goal, I need a 4 somewhere. And I don't have any 4s yet. So maybe splitting the fraction might be a little bit premature. I need to have that 4 there. So let's continue onwards. Well, I hope you guys can see that we have a whole bunch of double angles. And we have formulas for that. So sine of 2x, I know is going to be 2 sine of x, cosine of x, another cosine, plus, and then cosine of 2x. We have 3 variations. Which one do we choose, right? Which one's the right one? And again, there is no real wrong or right answer. You just got to be clever and you got to be, smart about things. Since I know that I have cosine as in my end goal, and I want secant eventually, and secant is the reciprocal of cosines, in my mind, this problem has a whole bunch of cosines. So I'm going to keep things in terms of cosine. So I'll use the one variation that only uses cosines, which is 2 cosine squared minus 1. Always use parentheses when you substitute. All over sine x, cosine x. Let's just go ahead and clean up some basic algebra. So this is 2 sine x cosine squared x plus 2 cosine squared x. Let's do the sine first. Sine x cosine squared x minus sine x all over sine x cosine x. Hey, we have like terms here. These guys are 100% identical, so I can combine them, and that is where we get our 4 from. Since I now have the 4 that I want, I think it's going to be okay, be safe to split apart the fraction, because I know eventually I want 2 separate pieces. And I believe if we played our cards right, that should take us to it. Because here a sine will cancel, one of the cosines will cancel, the sines will cancel, and we're left with 4 cosine of x minus, and what we're left with here is 1 over cosine, which is secant, which is precisely the right-hand side. Right. So, I mean, the proofs, it's the same concept, except it's just you got more puzzles, more pieces to play around with. We got these double angle formulas and these half angle formulas. Let's see what you guys can do with the half angle formula. Let's do an evaluation example. Suppose I ask you to find the exact value of sine of 22.5 degrees. So since I use the word exact, that means no calculators, no decimals. I want a fractional answer. Now, of course, 22.5 degrees is not a special unit circle angle, so we're going to think of the special unit circle angles. So in terms of degrees, because that's what we're in, the special angles are 30 degrees, 45 degrees, 60 degrees. Now, we've just learned sums and differences, but now I'm adding on doubles and halves. So what you should be thinking of in your mind is, is the thing that I'm dealing with, is it the double or the halves of any one of these special angles? And I hope everyone can agree or can see that 22.5 degrees is 45 over 2. That's exactly half as much as 45 degrees. So there we go. That's exactly what I'm going to work with. So I know that sine of 22.5 degrees is sine of 45 degrees over 2. So that is my special angle. So notice how the 45 is above the over 2. Is in the numerator. So in the half angle formula for sine here, this is where I'm going to plug in the 45. So it's the 45 that we're actually using. We're not using the 22.5 anymore. So just following the formula. So this equals plus or minus the square root of 1 minus cosine of 45 degrees all over 2. We're going to keep the positive because 22.5 degrees is in quadrant 1 and sine is positive in quadrant 1. So that's going to be what? The square root of 1 minus. Now, since I gave you since we're using a special unit circle angle, we should be able to figure that out. So cosine of 45 degrees is 1 over radical 2, which rationalizes into radical 2 over 2. Notice how inside the radical, it's a compound fraction. So lots of different ways to simplify compound fraction. I like to clear the fraction by multiplying every single term by the LCD. And the LCD in this case is simply a 2. So if I multiply everything by 2, I get 2 minus radical 2 all over 4. Properties of radicals. If you have a radical of a fraction, you can take the radical of the numerator and radical of the denominator separately. There's not much you can do in the numerator. 2 minus radical 2, that's whatever that is. But since 4 is a perfect square, we can go ahead and take the square root of that, and that's going to give us the square root of 2, the square root of 2 minus the square root of 2 all over 2. That is the simplified form. That is the exact value of sine of 22.5 degrees. Pretty neat. What other questions did we do yesterday? What other questions did we do in Unit 6? I asked you to find one trig value when given another. So we did stuff like, find tangent of u over 2 if the sine of u is 2/5 and u is in quadrant 2. So same spiel. I gave you a specific trig value, so you can go ahead and draw a triangle. Angle U. Sine, opposite of hypotenuse, is 2 over 5. And Pythagoras' theorem, that's the square root of 25 minus 4 is 21, right? I want a tangent of U over 2. According to the half angle formula, there's 2 versions, and it really doesn't matter which version you use. You can use this one or this one. It doesn't really matter. I'll just use, I don't know, this one because it comes first. Why not, right? That's my total awesome logic here. So I know tangent of U over 2 is going to be 1 minus cosine of U over sine of U. 1 minus, now cosine of U, I can just read adjacent over hypotenuse. Radical 21 over 5, but you always have to be mindful of what quadrant you're in. They tell me U is in quadrant 2, and I should know that cosine is negative in quadrant 2, over sine of U, which they told me it was 2/5, and since we're in quadrant 2, it's positive. So you just go ahead and simplify, just do the math. So that's what? 1 plus radical 21/5 over 2/5. This is a compound fraction. Simplify it however you want. I'll simplify by multiplying by LCD, which is 5 in this case. So that gives us 5 plus radical 21 all over 2, right? So this whole section is all about, hey, can you follow instructions? And can you apply these new formulas to old things? I hope none of these questions are new to us. We've done these questions before. It's just not with these formulas. Let's just do 2 more examples here. Say I gave you, I don't know, suppose I asked you to write sine of 2 cosine inverse of x in terms of x only, right? So this is what we discussed yesterday. Anytime you see an inverse trig function, you think of angles, because that's all an inverse trig function gives us. So we should know that cosine inverse of x should equal some angle such that the cosine of that angle is x over 1. So we have an exact trig function. We can draw a triangle. I hope you guys are sort of feeling like a sense of deja vu. Man, everything's the same thing. That's all math is, applying the same concept to different pieces, to different tools. So adjacent over hypotenuse, and then Pythagoras' theorem tells us the missing side is 1 minus x squared. So now I can answer this, because if I let this cosine inverse of x equals this theta here, then our problem, sine of 2 times cosine inverse of x, is simply sine of 2 theta. And we do have a double angle formula for sine. That's 2 sine theta cosine theta. And now that we have a complete triangle, just plug and chug, just simplify, right? We can just read it. So 2 sine of theta, according to this picture, is the square root of 1 minus x squared over 1 times cosine, which is just x. I like to put monomials in front of radicals, so I'll squeeze that x in front. But there you go. There's the expression of sine of 2 cosine inverse of x in terms of x only. It literally is the same problem we did yesterday, except, well, different formulas, different tools. So the problems like this, evaluate sine of 2 theta given that the cosine of theta is negative 2/5 and theta is in quadrant 2, should not be a challenge for us. It literally is what we've been working on forever. Hey, they give us a trig ratio. You can draw a triangle. I ignore the negatives. Cosine is adjacent over hypotenuse. Pythagoras' theorem says the remaining side is square root of 21. I want sine of 2 theta. That's 2 sine theta, cosine theta. Hey, I have a complete picture, so I can just plug stuff in. I hope, like, you can see that this is just automatic. We're on autopilot now. So sine, opposite of hypotenuse, is radical 21 over 5. We're in quadrant 2, so sine is positive. Cosine, adjacent over hypotenuse, 2 over 5. We're in quadrant 2, it's going to be negative. and then you just multiply straight across. What is that? That's negative 4 radical 21 over 25. So easy peasy problem. So in this section, you're just going to be asked to evaluate and simplify using these, quote, new identities, the double and half angle formulas, but the actual problems you're asked to do, evaluate sine of 2 theta given this information. Right sine of 2 cosine inverse. These types of problems are the same things we did yesterday, the same things we did in Unit 6, just with new identities. So good luck. Give that a practice.